will start later, but we will start. On this, it's supposed to be a workshop, but we don't have. We have only a slot of 30 minutes, so it's not enough to do the workshop. But we will show you how we generate or how we are generating ZK proofs now using PIL2 continuations and aggregation. We have worked on the last month on on what we call THISC and Proofman. It's our new products. We are Xavier Taulé and Xavier Pinsach, myself, from Polygon. And I will start to explain some quick and basic concepts about virtual machines and about witness computation and related things. So a virtual machine is a machine that executes a program, with public inputs and other inputs that can be public or not, and give us a result. But when we are talking about ZK virtual machines, we can get the result, but we want also a proof that the execution has been generated correctly, right? So a ZK virtual machine, the inputs are a program, public inputs, a proving key that we'll explain later on the next slide, and the output will be the result, and also the proof that verifies that the execution has been generated correctly. And we have also a verifier that, given the same public inputs and the verification key and the proof generated by the previous ZK virtual machine, accepts or rejects the proof. Okay. And here there's the workflow. There are specific part, the setup part, that it's run only once. That given some error descriptions, error means algebraic intermediate representation descriptions, and constraints, and some constant data, and some setups about related to the prover, generates a proving key to be able to generate the proof, and a verification key to be able to verify the same proof. Okay? That's basic concept. If we dive in the ZK virtual machine, we see that we have 3 stages, 3 phases. The first one is the execution that gives us the result itself, the result of the execution. Then we have a witness computation that from the execution generates some inputs. That inputs generates some traces that defines the witness. And then after this, we can, with the witness generated, we can prove it and generate a proof, okay? If we dive in on the witness computation part, this is a schema, is a sketch of the witness computation of the current Polygon ZKVM, where we have a big matrix, a big buffer, where we store all the related data of all the state machines that are computed inside the ZKVM. These are examples: the main data, the main traces, the ROM traces, the memory, the binary, the arith, or all the other ketchak. Okay, so if we use a public input that generates, for example, a lot of access to the memory, we will fool the memory trace, and we will not be able to generate the proof, right? Because the memory is almost full. Then if we generate more memory accesses, we will not be able to generate the memory. So this is a limitation. In the current ZKVM, there is that limitation that we cannot, we have a limitation about how many rows we are generating when we are computing the witness computation. And here is where it comes the concept of bad cops. Bad cops means variable degree of composite proofs, where what we want is to generate as many traces as we need to execute a given input, okay? So in this sketch, you will see that the main state machine, generates 2 instances on the left. The left main 0, main 1 generates 2 instances. The ROM needs only 1 instance. The memory needs 2 instances, the binary, and so on. So we are able to generate as many instances of a trace that we need. This is a change because if you see in the previous slide, after the witness computation, we have only a big buffer. That buffer is the input for the proof, and the proof use only that buffer and computes the proof. So in the bad cops, what we are generating is a trace for for each state machine, and the proof system or the proof backend has several inputs, and that several inputs generates as many proofs as we need, as many proof as instances on the Windows computations we have generated, okay? And then here appears a new concept of aggregation. Aggregation is a process to take n proofs and generate only a single proof from these n proofs. It's a recursive process that we aggregate like a binary tree, yes? So we take the pi 0 with pi 1, we generate a new proof, the pi 2 with pi 3, we generate a new proof. These are also aggregated recursively and so on until we get only a single proof. Okay, so the last months we have been working with the THISC. THISC is a new project that is a virtual machine, is a ZK virtual machine from Polygon. This is the repository, you can check it if you want. This is work in process, is almost functional, but we are still work in process on some state machines, precompiles, and so on. The functional specification for this is that a user can be able to write any deterministic program in Rust at the moment in Rust, and automatically convert this program in a proof, okay? So we have only 15 minutes, so.
Work? Yeah, hello. So the idea is that we will do a quick demo. We will show you, we will take a simple Rust program that does n number of SHAs, and we are gonna generate a proof, and we're gonna explain briefly like all the different pieces that that compose ZISC. So let me jump into the code. I'm gonna show you first the repos. You could reproduce what I'm gonna do, although now we have like several steps pre-computed because we have just 15 minutes, so otherwise we would not have time. So great, the screen's showing. So the main, the first and most important repo is ZISC. That's this one I'm showing. But there's 2 more repos that are important. So ZISC is, as Xavi explained, the program that allows us to prove any Rust program. But then we have Pilch2Proofman, which is a repository that allows us to generate the proofs. And then we also have Pilch2Proofman.js, which allows us to generate the setup that Xavi was explaining before. Right now it's in JavaScript, but we are migrating it to Rust. And that's one of the pieces that's missing. So if we check the docs, the first thing that says there's an installation part in which it shows all the repos that you need to install, all the preliminaries that you need to do. This is already done on this laptop, so then we can jump directly to quick start. And the first thing it says, okay, so we're going to run cargo sys SDK new hello world. And now I'm going to do a cargo sys CDK new hello world. So now we've created a dummy program that's basically the SHAs that I was mentioning before. We can jump in. Yeah, well, and the next, I can hold it. And then we simply need to run cargo sys run release. Basically, what this does is it will process. It will convert the Rust. It will break down the Rust program in RISC-V instructions, and then we will convert those to CISC instructions. There's a one-on-one relation, and right now we're going through RISC-V, although we're not close to that. Maybe in the future we will explore different alternatives, such as Cradle Lift. Okay, so now there's, I need to carry out sysg build release. Great. So now I'm missing the input, so I'm going to copy it from another file. So now it's building the crate. Okay, now it's built. Now we're going to run it, and we're going to generate the L file, which contains all the instructions. And also, I think that it prints the SHA and the SHA output, and now the next steps will be the setup, which I'm going to completely skip this part because we don't have time. So I already have this, and I'm going to directly jump to the proof, which is much more interesting.
What we have done now is to convert a Rust program into RISC-V 64 bits, and then to convert these instructions to sysg instructions. So
basically, I'm going to run the proof, and I'm going to explain, and while it's running, I'm going to explain you how everything organized. And so the first thing that's happening is that now it's loading the setup. And here there's two parts. There's the setup of all the different state machines that we are using, and then there's all the aggregation part that I'm going to explain while it's running. And then the next part is the program will execute. Basically, we are generating several instances. Here you can see that proof instances. So for this example, there's like 21 mains. There's a lot of binaries. Binary extensions that are not the basic operations. There's also we're performing range checks. And at this point, the prover starts working. Basically, the idea is that we have, instead of one huge monolithic proof, we break down in small instances, and then we prove each instance separately. And since this will result in like many proofs, right? Because we will have one proof for each instance, but we just need one single proof of the program that we are executing. So what we do is we first generate all these instances, and then we aggregate them together, and we generate one single proof. So the idea is that all the instances run at the same time and share the same challenges. So at each stage, all the instances synchronize because they are connected with each other, right? So they synchronize, and we get one single challenge that is distributed across all the different instances. And also one very important part that was just showing before, it was here, it was saying computing with STD-SAM. Basically, we rely a lot on the lookup protocol. So the way that there's different instances that either assume or prove. So we have in PIL what we call air group values, so that we have different instances that they are proved independently, but then so if two instances are related, one instance will prove one thing and the other one will assume the same thing. So at the end, what we're doing is we will check at the end of the proof that what one instance assumed and what the other proved matches. Basically, like to simplify it a lot, we just need to check that the sum of those values is 0. So if we check what's going on, we compute fry. Right now, you can see right now we are doing a fry for each of the instances, but in a future, the idea is that we will have either multi-fry or some of the newer protocols that were explained in last CK Summit, like we're. And here what's happening is we're already on the aggregation part. So will aggregate all those proofs together and in a tree fashion. So each instance has its own air group values that I was mentioning before. They bring some part of the assume or some part of the proof, because you can have multiple instances of the binary, for example. So what we are doing here is, firstly, we are compressing the proof to shrink the size, because we are based a lot in what we did in the ZKVM, that we want our system to be able to aggregate an infinite number of instances. So to do that, what we need to get to get that all the proofs have the same size. So then we have our recursive circuits that can be merged together, and we can add continuously new proofs. So first, it's compressing. I'm going to show you the circuits because I think it's interesting. I think I'm going to jump directly to the final. Basically, there's two main circuits. The first one is the recursive two, like this one. Basically, what this circuit does is it takes two proofs, proof A and proof B, and it generates a new proof that is proof AB, which is it has exactly the same shape and size as proof A and proof B. So you cannot distinguish between them, but it allows us to. So then we will be able to aggregate proof AB with proof C, for example. And the important part of this circuit is that I was saying. So we said that all instances share the same challenge, right? But we need to ensure that. We need to make sure that our proof checks that this is right. So the way we build the global challenges is that we build a tree of all the, for example, for the first stage, we got all the roots of all the instances, and we build a tree. And then when we aggregate, here there's this aggregate values null. We basically reconstruct the tree as while we are generating this recursive proof. So we are not only generating a new proof that verifies A and B, but this proof also has as an input, as an output, a new accumulated part of the global challenge. So then the recursive, then we keep doing that, and not only for the global challenges, but for the different air group values. And let me check. So it's finishing with the recursive one. I'm gonna let it run. Yeah. So yeah. In the meantime, I can also show the peel and other stuff, or I can show the final, because at the end I think it's interesting that. So we aggregate proofs, and then we need, in the final one, the important part is that we need to verify that the global challenges were valid, and that the global constraints, which basically are the assumes I was talking before, that there's like different machines that are how to say this, they are assuming or proving some stuff, and we need to make sure that the sum matches, right? Because there were two independent proofs that were supposed to be connected, but we need to check that connection is done properly. And this is done here at the end, and this is very important because what happens is that we will be able to generate one single proof that verifies all the instances and also make sure that all the instances are properly connected. And so I think that's pretty much it. Yeah, I can show you a peel a bit. Do you want to? No, so here, for example, this is the peel we're using CISC, and then we have different state machines that Xavier was showing at the beginning of the talk, like the ROM, binary table, and all this can be found in here. State machines, there's different state machines, arith, binary. I'm not gonna jump into the peels because they are a bit.
Yeah, This part is basically the arithmetization part that we are using the language, the PIL language. PIL language is a polynomial entities language where we are defining, in this language, we are defining how the errors are, the errors, the constraints, and the constants. So PIL, we are using right now, currently where you're using PIL2 it's very different than PIL1. You can find the repo in PIL2 compiler is the repo. You can find it. You can find a link inside the THES repository. And from the PIL files, we are defining all this stuff, and then we generate a PIL-out file where that is a binary file to store that arithmetization part that we will use to generate the proving key and the verification key to generate the proof. Basically, it's that. If you need something more info, we will be around here because we have only 1 minute. So
now the final proof is being generated, so we can verify it. So at least show that the final proof verifies. And now we run it. And basically, it says that verification. Okay, so basically, we have a proof that could go to Ethereum that program was executed properly. And well, this could and now it's been run on sequential mode, but this could be also run in distributed mode, which would be much faster. Or also there's GPUs that's...
Yeah, we are working on that. Specifically on the distribution part, we have very good results, very good results. I think there is a branch in the ZISC, I can't remember the name of the branch, but we have very good results on the distribution part, and in the next weeks or months we will merge it on develop. And I think that's it.
Yeah.
Okay, thank you very much.